Hello, everyone. Thank you very much for being here today. My apologies for not being able to make it. I've been a little bit sick for the past few days. But today I'm going to be talking about some of the work that we have been doing in regards to foundation models and some of our coarse resolution satellites like MODIS, ABI, etc., and how we have been kind of looking at some of these foundation models and pre-trained embeddings. Just to kind of emphasize the things that we have been focusing on, at least from this perspective, as in to find models that can be adaptable, to move across some of the sensors that we're working with, to make them accessible. How can we, instead of having to load these huge weights, huge models, how can we load them from commodity-based hardware? How can we share some of these embeddings? Also trust, not only kind of pre-training some of these models or trying to get some of these embeddings, but also understanding how much can we trust them, to which extent are we producing better science? And last but not least, how do we validate some of these models? How can we know just by looking at some of the embeddings, some of these pre-trained features that this model is going to be used for actionable results that are going to produce better science? From our perspective, is not only improving some of the results, is actually producing better science and getting there faster. Part of that kind of inspired some of the SatVision framework, and is the main reason was because we had a lot of gaps in terms of using core resolution data. At the time, we have all these kind of pre-trained CNN weights that we would use. Resolution was kind of a challenge with many of the architectures we had. We started then exploring transformer-based weights to use with MODIS data, with AVI data, and we were still lacking some of the features and some of the textures that we normally have from models that we were just trained from scratch. So being that there was just no available pre-trained models, uh, we started then producing kind of our own pre-trained models. And we started with CNNs, then we started moving to more of like kind of the self-supervision side of things. And then we find kind of this mix of having better performance by using self-supervision and kind of large amounts of data to train some of these transformer-based models. This gap that we have been kind of trying to close the loop is we had many tasks that had like many years of data. Like we have sensors that, for example, motors that have been tracking some of this data since 2000. So we needed to kind of be able to reuse the same framework to do some of the operational tasks that we need to work on. So that's kind of how the SatVision framework came into play. The first product was SatVision SR, which is basically a pre-trained Swim V2 model using MIM as kind of the reconstruction and kind of learning process or framework using MODIS data from the software reflectance data set. How this started was we basically sampled across the globe is different types of data sets. And the questions that we had was, okay, well, how far can we go? Like, what is the good balance between the number of parameters that we need for a model, but then also the number of chips or that images that we need for pre-training our models? So we starting on kind of understanding some of these laws of scaling some of these models. So we trained a base model, which was basically 80 million parameters, 84 million parameters with 26 million chips and 2 million chips, just to kind of understand different convergence processes and how those would affect our downstream task. We also had a 3 billion parameter model, which is kind of the one that we have been using for some of our operational projects and using 26 million tiles to train it. This one was basically kind of randomly sampled across the globe, across time, just to get different types of seasonalities, different types of surfaces, etc. But then kind of using just clear sky imagery. Now, as we finished training this model, we kind of started understanding some of the benefits. And we quickly saw that difference here is that when we use some of these pre-trained embeddings to train some of our downstream tasks, we were seeing that just by having 10 samples, we were able to get conversions very quick to an actionable answer. To get better science, we definitely needed to add more labels, but to get a quick answer to understand if this was valuable or not, we only needed a few samples. And this is huge because then we didn't need to spend a lot of time on creating labels. We didn't need to spend a lot of time on producing some of that training data. We would know right away if the architecture and whatever the code that we were attaching to this could have a good impact or could be beneficial to the downstream task that we had at the time. So we went from having to wait maybe a month of getting training labels to being able to get an answer in just a few minutes, a few clicks of labels that we had to produce. And that was solid. Like we were actually getting actionable insights right away, but the science and producing better science, it was not yet justified. We were getting way less errors when we used some of these pre-trained embeddings, but we were still getting comparable results when we gave the same chance of success for both the training from scratch model and some of these pre-trained models that we had available. So the better science argument was kind of still there, just because both ends were kind of producing similar results, similar science by the end of providing both examples with the same amount of representative data for the task. But then again, we had many other downstream tasks that we wanted to improve, we wanted to benefit from, particularly when, in this case, focusing more on the cloud side of things. So many of the foundation models that we were trying for this task, they were clear sky imagery. So when we were trying to reconstruct some of the cloudy scenes that we need for understanding cloud mechanisms, we would just fail. We wouldn't have any meaningful embeddings from them. So that's why we trained SatVision Toa. And a similar question we were trying to answer here is, okay, well, we now have clear sky and all sky imagery that we're combining to get representative embeddings, that we're trying to reconstruct some of these imageries to extract useful info. How much data do we need, and how big does the model need to go? So we use 14 MODIS bands from the MODIS sensor, and then we scale between the number of parameters. We went from 84 million, 700 million, 3 billion parameters, but then also scaling with that the number of data. So we had 2 million chips, 26 million chip, and 100 million chips. And just training different models and different sizes to understand how scalable were the architecture, but then also how much data do we need. Do we actually need 100 million samples to pre-train a model? Or do we actually reach a plateau using all that data? And the answer for that was yes, we actually reached a plateau. We actually reached an area where we saw that there was deficiencies in the model if we use less than 50 million chips for a 3 billion model. But we also saw that there was a plateau between 50 million and 100 million chips that wouldn't provide any actionable benefits to the SatVision TOA model. In addition to that, we did see that increasing the number of parameters did improve the model performance, and we trained many iterations of these in the Frontier supercomputer from the Oak Ridge National Lab, and we kind of saw how these scaling laws looked, and we understood kind of how what the balance is between the number of parameters and then the number of chips that we needed to train some of these self-supervised models. Now, we did have a task that we need to tackle. Both SatVision SR and SatVision Tour were single time steps. The cloud properties that we were trying to extract to build our digital twins, we needed multi-temporal information. And this is where kind of the next step came into play for SatVision Pix4D. In this case, we have a SatMA-based model that is then using multiple time steps from, instead of MODIS, ABI data, so we can have and track clouds, convection, many of these features in near to real time timestamps. Okay, so in this case, we're trying to reconstruct some of the cloud scenarios. So we are using the full resolution of GOES-R series ABI observations, using all of the channels available, a total of 16, and then using 7 sequential time steps with 20 minutes cadence to understand and track some of these convection mechanisms and some of these cloud formations as well. The model was actually optimized for this kind of nowcasting task that we can leverage for, let's say, clouds, convection, moisture, surface features, etc. Now, given that we're tracking convection as part of this kind of model, and we want to be able to reconstruct some of these with uh, extreme care, we then proceeded to have a more stratified data set. SatVision and TOA, we basically just stratify across, do we have clouds? Do we not have clouds? Do we have this type of land surface? Do we have this type of land surface? From there, we move on then to stratify not only between what is there, but then also what type of clouds do we have? Do we have high clouds, high mid clouds, low clouds? what kind of convection systems do we have? Do we have short convection systems? Do we have long convection systems that can last for more than the time frame that we're talking about? So we then produce this stratified data set so we could focus then on rebuilding and kind of reconstructing some of these convection tasks as well as part of the learning process of the model. For the convection, we use the toucan data set as our mask, which includes both where the convection is, but then how long is it going to be, or basically tracking the convection system life stage. And then also using some random tiles so we could include both clear sky, but then also different surfaces that do have also like all sky imagery as well. Now, difference from the previous models, we were able to use generalized losses for reconstructing some of these pixels that we have with MIM. Now that we're modifying this ATME architecture, we had to focus on kind of also a different loss. So we heavily modified this ATME architecture. First of all, to include more than the three channels or bands that are included right now. We now can support flexible number of bands. We have a pre-trained model that has 16 bands, but we can use less than that or increase the size of them. We also then have dynamical spatial position encoding where we can then use different types of tiles, different sizes, etc., which would be very important when we're tracking different types of features across the ABI imagery or the other sensors that we're also tackling at this time. Flexible temporal embedding. So now we can use, instead of one timestamp, we can have 7 timestamps. We can have 10 timestamps. We can have a single timestamp and you're just extracting the embeddings for that particular timestamp and just using that projection for whatever task we have. We also have a dynamic embedding projection module where we kind of focus then on combining the spatial and temporal features that we're learning and then using those as part of our task. Finally, the idea was to make it scalable and flexible. So we're then supporting even the number of channels, number of time steps, but then we're also serving it as part of a Triton server, where instead of having to load the weights from this model and kind of be able to use it on commodity-based hardware, we're then serving some of these weights as part of requests that you can do through HTTP. In regards to the loss function, we noticed right away that we were not getting convection system texture. Like we were not getting some of those features. So we had to modify the loss function to track some of these features. We combined basically the Charbonnier loss for general pixel reconstruction, the Soviet gauge loss to again then get that sharpness of texture that we needed from clouds, but then also then an SSIM based loss function to then get kind of that structural similarity between different resolutions. And this actually helped with the reconstruction process to get better and more informative embeddings. So different ways that we have been kind of validating our embeddings. First of all, just using unsupervised clustering and then getting some of the strips, getting some of the embeddings, and then just clustering and seeing if we can have different types of features clusters. We have different type of like cloud top heights in different clusters. We can actually, from just the embedding, see different groups of different cloud types, different surfaces. We actually have clear sky that have been kind of positioned in the same location, different surfaces within the clear sky being clustered as well, that we are actually extracting some of that information on. So there's kind of a good way of saying, okay, well, at least the embeddings are representative of what is different. But we don't only want that. Like we need to kind of move on then to produce some of the downstream tasks. And so the main challenge that we had is many of the baseline models that we have were just not performing well on their state of the art right now. So we are able to increase from 0.4 to 0.6 mean IOU just by using SatVision Pix4D, the 3D cloud reconstruction task, which in this case, we're basically trying to find where are these clouds, but then also in which height are they actually supposed to be at. So basically a binary segmentation task with the reconstruction on these particular levels where they are. The second task then was then, instead of just reconstructing where the cloud is going to be at, reconstruct where the cloud is going to be at, but also give me the type. So we have eight different type of cloud types that we can then use. And the interesting fact is, just by using 500 labels, we were able to match the performance that we had with baseline models. And then as we kind of give it additional labels, we were able to surpass some of the performance going from 0.06 from some of the different cloud types that we have to then 0.4 right now as we're kind of been testing the downstream task. The final downstream task that we're kind of working on right now is then the convection nowcasting, which is basically tracking the life stage of these convection systems. When is the convection going to end? how long are we going to see it, how far can we track it, etc. So we're just tracking both position, but then also time for some of the convecting tasks. And we're kind of working on that, getting some preliminary results right now that we're producing as part of using SatVision Pix4D. So as a summary, like we have many tasks that had the need for this. So we kind of had all these tasks. We knew we kind of needed to kind of have something pre-trained. So we start with CNNs, transformer-based. Now we have this multitemporal transformer-based model that we're using for some of these nowcasting tasks and single time step task. If this is useful to you, just feel free to reach out. I'm gonna leave my contact in here. Feel free to just kind of email me, and I'm happy to share the weights, happy to share any of the code that we have. What we have been doing is kind of basically testing both loading the weights from, let's say, a notebook. People can just use it that way, but then also serving it through a three-tone inference server where instead of having to like knead the weights, um, to load it, all the hard part of getting the embeddings can be done at the three-tone server side of things, inference server side of things, and all you get back are basically kind of your weights, or the kind of feature embedding space that you need to your downstream task. So feel free to reach out. We have seen a lot of kind of improvements from this. We can kind of justify getting better science, and the idea now is to just kind of make it more accessible so we can continue using some of these. So any questions, feel free to email me. And again, so sorry for not being there. Hopefully you have a great conference. Take care.